Excellent. Okay. And now, Jake, the idea is to go through each section and just say what it is without elaborating very much. Just imagine that you were typing in comments for the code as you go through each section, but say what each section is. You know, highlight it with your cursor, and then say you know, how you would comment that block of code.
Yep. So yeah, so first off, it starts off with taking each of the input values, setting them to your global variables. And then once you have your global variables set, you calculate various constants like sedimentation and diffusion based on them. You create your file that you input, and then you create three 2D variable or 2D arrays that represent the x, y, and z coordinates for position, velocity, and acceleration for each individual particle. You check the number density. This isn't actually really used in the system. Give each particle a random position, uniformly distributed throughout the volume. And then you give each particle a velocity as well. In this situation, it is a constant magnitude across all of the particles, but with a random theta and phi angle. And then you convert the polar coordinates to x, y, and z coordinates with set velocities. You then calculate the acceleration based on the position of each particle relative to the cover slip, so the electrostatic interaction between those two. And then you set up some initializations here, like you set time to 0, set x and y arrays to 0. You write your initial variables. So if you would like to write the positions and velocities, you can do that. But in this case, it would just essentially just give you time to 0 and then the particles that have landed at 0. You set your delay. If you are using a delay, set it to 0 for now. And then in terms of layers, you split the volume into 100 slices, and then so that way you can count the particles in each slice at each time step.
Can I stop you just for a second? Go back to the vertical velocity. And so you use the electrostatic attraction of the cover slip as a source of acceleration for your particles. And this calculation also includes sedimentation, is that right?
I believe sedimentation is calculated with the velocity. So
Okay,
sedimentation is, at least the sedimentation value is a unit of 1/seconds. So I think that what I did was, where is the set velocities function? Yes. So yeah. So this is, I multiplied it by gravity. So that gets meters over seconds, and then you subtract that
so
from
what I was going to
whatever.
say is that you had a, a vertical acceleration that was due to electrostatics that you included explicitly. There's an implicit acceleration due to gravity, but that
Yes.
comes into your sedimentation calculation because the sedimentation constant that you're using includes the gravitational constant and the mass of the particle.
Yeah.
So you have some Galilean physics going on in these particles, and presumably you're handling their acceleration due to gravity in each time step of the calculation with this sedimentation term. Okay, so let's go back to where you were. I'm sorry to have interrupted. I just wanted to make that point.
Yeah. No, that was a good point. So now we get into the actual iteration. If the number of particles that have landed exceeds 95% of total particles, then just stop. All the variables are updated here in this iterate function. So first position is updated based on the velocity times the time step. And then checking each variable or checking each particle. If a particle is within the diameter's range of the cover slip, then it attaches. So basically first check the x and y coordinates of the particles to make sure it's within the boundary. If not, then move it to so it is within the boundary. using periodic boundary conditions. Set the position, the Z position is 0. The cover slip is at the 0 position, going from 0, 0, 0 in one corner to LL height in another corner of the volume. This distribute energy was an attempt to homogenize the kinetic energy or to distribute it that's lost when it attaches to the cover slip. But right now, it essentially just sets that velocity to 0 and then set the acceleration to 0 as well. If it's not within that distance, then just make sure the periodic boundaries are met. And then also for the height, if it's touching the wall or if it's past the top of the wall, then have it bounce back down. Check the or update the velocity with 1/2 step of the time step. Update the acceleration again based on the electrostatics of the cover slip and each individual particle, and then again update the velocity with the second half step. And then as well update the polar velocity variable based on the new magnitude that was calculated here. And then lastly, update the time. And then here, if you're using a delay time, if the current time has met the delay time, that at that point you want to update your delay particles count so that it can be an effective 0 starting from here. And then every 10 time steps here I have set, it writes your current data to your output file. It finds the number of particles at every single layer and records that to this array. The X array is the current time, and then the Y array is the current particles that have landed on the cover slip. And then after the this is for every time step. In order to simulate Brownian motion, you want to update your velocities with a different random angle, and then that random angle is determined based on this randomization factor that you have. And then this last bit is just for me, just to print out the percent completion, so you know if it's stuck or not. And then last, these commented out bits are just from the data analysis file that was used to visualize the data. But this is kind of an example. This just says find the first order rate fit with the raw data, find the R squared between the two, and then plot those two graphs.
Excellent. So that was very good. Now, I think one thing that would be good for you to do in Delhi as you start to work on the program is return to this Zoom recording and go through the program itself and try and transcribe Jake's comments about each of those sections and write them down as comments to yourself as to what each of those parts of the program does. And if you can, going through the exercise of really defining each little subsection of the program will help you keep it straight. And of course, once you start to use the program, this will become second nature to you. For example, if you were the one who wrote it, I'm sure that, the last thing you want to do is waste your time commenting it because you understand every line of code that you wrote. But you're coming to this as something working with somebody else's code. And one of the things you'll have to do is explain it to yourself. And I think that actually putting comments in the code itself will help you a lot. Also, it will help Aiden as well, because at some point you'll probably want to, I'm sure you won't be able to resist wanting to run a few simulations yourself once you see how this is working.
Yes.